Okay, we are going to do 8M3 lesson 1. We are moving on. We are on a new unit. We are going to grow and expand on what we've already learned in 8M2. We learned about rigid transformations. In 8M3, we're going to expand that a little bit, and we're going to talk about some similar transformations. We're going to talk about similarity. We're going to talk about what you get when you stretch and shrink objects, and these are called dilations. And we're just going to get a little bit into it here in lesson 1, not too deep. We're just going to kind of get a sense of what they are and give you some homework help as well. So let's cut over then to our sketch pad, and let's learn a little bit about these guys. So let's here we go, window, sketch pad. Okay, so this is these pictures here are from your lesson, and you went over these, I think, in class today, and we talked about the idea of similarity, and again, before we talked about rigid transformations, which maintained size. Okay, and those were, translation, reflection, and rotation, and so these are all maintain size. But now we're going to add one more in, which is called a dilation, and this has to do with things that are the same shape but can be different sizes. So let's just talk about this. So let's look here at pair A. We can get the sense that if we look at this smaller object and we go to the bigger object, that these are indeed the same shape, right? You see that those are the same shape, but different size. It's just like we took this and this is like it grew up. It became its, older sister, older brother. It became a kid and became a dad, but it kept its same shape. Now let's look at pair B. So this would be yes, this is a dilation, which is our mathematical word for just shrinking or growing an object. Going in this direction too is a dilation. It's just shrinking. This is growing. Going here is grow, and go here we shrink. And so those are both dilations in different directions. Now as pair B, we kind of look at it, we say, yeah, those guys got kind of the same angles perhaps, but if we go from here to here, we've kind of stretched it taller. We've stretched it this way, but we left it the same in this direction. So this is not the same shape. This here is a square, and this here is a tall rectangle. So this would be no. So that was yes, that's no. C, yeah. This is still a dilation, but it didn't get bigger or smaller. It just kind of stayed the same size. And dilations don't have to, they can be, those can be a shrink or a grow, but they can also just simply be the same size, and it is the same shape. D, what is this? Yeah, a circle, you take it to a smaller circle, this is a shrink. All circles are the same shape. They're all round. They're all perfectly round. So this is yes. And here we have, this is probably a dilation. We've rotated it. You rotate it, and then you've grown it. So this is a rotation, then a dilation. So this is not just a dilation. You can't shrink this or grow this and get to this shape. You have to grow it. You have to grow it, and then you rotate it. So that's two things. But it is, dilation is one of the steps in getting you there. Now pair F, this is a smiley face. This isn't a traditional shape, but yeah, this is a shrink. Now watch, I'm going to show you something here in a second that's going to help you see the difference between F and G. So F and G, this is looks kind of the same, but it's not a dilation because you grew it, you squished it in one direction, but not in both. So let's look at this. So if I can take an object like, we're gonna look at F right now. So this is my F, right? This is F. This is F right here. And so if I can take an object and I can shrink it in both directions. So that's kind of like when you're in a browser or on a computer and you shrink something from the corner, that's shrinking it in one direction. See how that works? That's shrinking it in one direction. And that gets me, to the original, that's the same. Now, this one, I can't do that, right? You can't draw from the corner and get the same thing. Now, I can drag from the top and I can squish it, but squishing it doesn't count. It has to be a drag from the corner, and I cannot do it. So you can't get from here to here. And similarly, I can't shrink or grow this guy from the corner and get that object. I can shrink it, I can grow it from the side and kind of maybe get close to the same shape. But this is not a dilation. So hopefully you're kind of getting the idea here. Shrinking and growing has to be in both directions for it to be a true dilation. So hopefully in class, when you went over this with your teacher, it all made sense. This is just kind of a general feel, getting an intuition about what is a dilation and what is not. So let's move on and let's start to talk about a little bit more formal of a definition of a dilation. So here's our informal definition. This is our informal definition. And it's same shape, different size. And we learned actually that it actually can still be the same shape and the same size. And that would be if we have a dilation size of 1. So any object that's the same as another one, they're congruent, in other words. Those are still dilations. But generally, when you actually dilate it, you're making it bigger or smaller, although technically you can keep it the same size. So a more formal definition of a dilation is when you take an object like this triangle. So we're going to take this triangle and we're going to map each point of this object to a new object. Okay? And we're going to do that by taking a center point O. And so if I were to dilate this triangle using center point O, which is often called the origin, each point P, so each point P, P, Q, and R, is going to be mapped to a new point, P prime, R prime, and Q prime, along a ray that you draw from the point, from the origin to the point, with a length equal to a scale factor of R and a length of R times OP. So let's just show you this, and then we're going to do it again, and we're going to use GeoGebra to get even more technical about it. So let's just say that we're going to take each point. We're going to use our vertices. And so I'm going to take a ray here, and watch how I do this. Whoops. I'm going to take my ray. Let's see if I can make it a different color, just so we don't get confused here. Yeah, there we go. So I'm going to take this ray, and we're going to double the size. So we're gonna take this ray, which goes from O, and let's just draw this in here. So if it was O, and this was point P up here, and this is point Q, and this is point R, I'm going to kind of make the points be far away to make this easier to show you. So if I take this point, and I'm going to double the length. So watch how I double the length. right? So now instead of OP, I'm going to OP prime. OP prime. So this is P prime. And now I can just, let's take that. So there we go. So we had OP is a length, if that's a length of 1, then OP prime is twice as long in the same direction. And we're going to do that same thing. Watch how I do the same. Whoops. I need to put a point out there. So let's put my point. Let's make it in red. Oh my goodness, I am like all out of control here. Yeah. Okay, I have to make my line. Make my line. Okay, there's my line. I doubled the length. Okay, so now let's make the line in green. Oh, where did my line go? Okay, here we go. We're having problems again. So we're going to put it right here. Now I'm going to take my point, make it blue, and put it here. And now I'm just going to go back and I'm going to delete my rays. So you're going to see. Okay, so that's my point 1. Now we're going to go and we're going to double the length of this other one. We're going to use we'll use orange, and we'll make it go from here to R. And we're going to double the length. And then we're going to make another point. And remember, this is similar to what we used to do when we did our our dilation or our transformations in AM2. We used some techniques, and now we're going to get rid of that. And now we have to double the length of our other side. So let's go from O to Q. And let's make sure it's the right length. And let's double it up. A little bit off. So it's not perfect, but we're going to try our best here to draw this so it's kind of here. You'll see it'll come out about right. I didn't use a ruler, so things aren't exactly perfect. So I made my rays. Remember, I made a ray from O to P, and then I doubled the length. I made one from O to R, and I doubled the length. And I didn't label my points, so let's just finish labeling up our points. This was Q prime, and this one was R prime. Remember? This was point P, this was point Q, and this was point R. So this is Q prime, R prime, and P prime. Now let me go and let's finish it up. Let's draw our final dilated object, and let's do it in light blue, and we'll just look and see what it looks like. So look at that. We have an object that is twice the size of our original object. It's called P prime, Q prime, R prime, and we used a technique to make sure that it was the same shape but a different size. And in this case, let's just be really exact, and let's finish it up, and let's say that our R equals 2, because we doubled the length, times 2. So every point from O to our original point, the dilation factor was 2. And so our shape is 2 times dilated. Okay? So let's look at this more exactly. So that's the strategy that you will always use whenever you dilate an object. It could be a triangle, it could be a circle, it could be a square, and you have to pick some points. And usually the vertices are great points to choose, just like with translation, just like with rotation, and just like with reflection, choosing the vertices to perform the objects on, or to perform the actions on, were always good choices. Okay, so now what we're going to do is we're going to go over to GeoGebra, and we're going to go straight into some homework help. Again, what did we do so far? We had a concept of shrinking and growing. We learned an intuitive definition of dilation, and now we've moved into a technical procedure for how you can dilate an object. And GeoGebra is going to be an easy tool that we can use to see how we dilate points or objects. And this is going to be your homework help. So this is your homework help. Okay, and so the question here, and I'm going to write it like the homework. Let there be a dilation from center O, that's this point here, point O, with dilation of B equals B prime, and dilation of C equals C prime. Now the question is, what can you say about the scale factor, which is also the dilation number, right? Question. Now I want you to think about that. Is this, so in other words, we had these two original points here, B and C, and we've done a dilation that caused the point to get moved to B prime, or mapped to B prime, and C to C prime. So the question is, what can you say about the scale or the dilation factor? Okay. So I want you to stop and think and pause. Now the answer to the question is that the dilation factor, the answer is it the scale factor. I'm going to use the word scale factor. Scale factor is what? Is less than 1. Why? Because it's a shrink. We are making it smaller. We are bringing the points closer to our center. So if the points come closer to the center, then the object or the points are being shrunk. And so a scale factor of less than 1, remember, if we go back to our rule, R is less than 1, that's shrinking. That's shrinking. Okay, so scale factor. So I know the scale factor is less than 1. And exactly how much? It turns out that if you measure it, B prime and C prime are exactly half of the way from the B. So our scale factor is hidden here. If you opened your eyes and you actually saw, I actually had it hidden right up here. It's 0.5. And notice how we can change it. So if you have 1/4, 0.25, that's a fourth. Here's a half, here's 0.75, and here's 1. They're right on top of it, right on top of B and C. Now, if my scale factor gets bigger, then my B prime and my C prime actually get bigger, further away, longer from each other and longer from the center. So this is how you can use, and notice if we have our 0.5 or our 0.5, the O to the B prime is on the same ray as O to B. It's on the same line, and it's exactly half the size. If it were to be 2, it would be on the same line as O to B, but it would be twice the size, twice the length away. Similarly, the O to C would be twice as far, O to C prime would be twice as far as O to C if the dilation factor were 2. So hopefully you kind of see that. We can kind of do something cool here. Let me just experiment here, and let me make these line segments really highlight it for you. Right, so our line segments are now also being scaled. So now we have, this is a scale factor of 0.5. Our I is smaller than H, but when we get that dilation, when we're dilating it and getting it bigger, then that line gets really big. Okay, so let me ask you a question. Let's say we had a scale factor of 2. Now, I want to ask you, this is also homework help, so think about this one. If OB prime is 10, then how big is OB? How big is OB? The scale factor is 2. Okay, so pause and try. Pause and try. Okay, so I assume you're back now. And so the answer is, for those of you who said the answer is 5, you are correct. And think about it. If the scale factor is 2, then what number did I have to start with to get to a size of 10? If my final object, my dilated object was 10 and my scale factor is 2, I needed to start with a 5. Because 5 times 2 is 10. I'm going to show you one more thing. And this is, we're just going to go to our dilated, this is, you can also notice you can dilate a triangle. So if I start here with a triangle A, B, C, A prime, B prime, C prime, or A, B, C, and I want to, well, we're going to hide the, no, we'll just leave it there. Yeah, we're going to hide our triangle real quick. So we have ABC. And now if we were going to dilate this thing 2 times, we would take each point along the line from O to C, from O to A, and O to B prime, and we would go twice as far out, right? So in this case, we have a triangle. We dilated our triangle, and we did this on the sketch pad, but here's a more perfect example. We took a triangle and we made it, we dilated it 2 times, about 0.0. So OC and OC prime is twice as far because, again, our dilation is 2. OA to OA prime, this is from here to here. O to A is half as far from O as A prime, or in other words, OA prime is twice as long as OA. And similarly, O to B prime is twice as far from O to B. And if we wanted to make it 3 times bigger, we get that. Now, what would happen if we made our dilation factor a half? Think about it. A half means smaller, right? So if we made it half, it'd be right down there. And our dilated object would be, whoops, what did we do? Okay, so let's select that object. And I just wanted to, how do we make it, how do we change its color? My goodness, I don't know. Okay, oh, there we go. Oh, well, we'll save that problem for now. Here we go. We'll just make it green. So our dilated object is now 1/4 the size, half the size, 3/4 the size, same size, and now twice the size and growing. So watch, if we kind of animate that, you can see that we're basically keeping the object in the same shape, different sizes, but every vertex is still right along the same line or along the same ray as if you drew a ray from O to each of the vertices. Pretty cool. Okay, let's cut back and let's wrap this thing up. So hopefully you now have a good sense of dilation, how to dilate an object, the concept of dilation factors being smaller or larger than one, smaller than one meaning shrinking, larger than one meaning growing, and then also have a simple technique for how you actually perform a dilation, which is going to be important as we lead into lesson 2, lesson 3, and beyond. I will see you tomorrow. Hopefully this was useful. You're welcome. And we'll see you next time on Dave Lipscomb's Math channel.